In part 1 of lecture 12, we will discuss input-output device basics. The operating system's main job is to serve as an interface between the user and his or her programs and the computer's hardware. This means that the operating system must be able to interact successfully with any type of input and output device that will be connected to the computer. This is not as simple as it sounds. Input-output devices differ widely in terms of function, design, and speed. Each type of input-output device, whether it is a mouse, a keyboard, a monitor, or a disk drive, may have a different type of hardware interface and will definitely need a different type of software interface. There is an element that has to be added to the mix. There is a strong push toward interface standardization. An example of this is a large number of devices designed specifically to work with SCSI or USB ports, and the push toward standardization applies to the software interface as well. Modern operating systems deal with this by becoming modular. The device drivers are designed to work through a standard interface with separate modules to handle device-specific details. There are essentially two interfaces between the application program and the input-output device, one hardware and one software. I/O devices have a controller that serves as an interface between the actual device and the operating system. The controller is the electronics that controls the input-output device, which is usually electromechanical. It is useful to think of it as a specialized processor with its own set of instructions and registers, and unlike the processors around which computers are built, its sole purpose is to control the devices that are attached to it. The device driver can transmit instructions to the device controller and receive back its status, telling it whether it is busy or idle. Depending on the type of device, data can flow in one or both directions. It is the device driver that communicates to the application process, usually through a layer or two of software. Whether or not this includes a file manager depends on the type of data and device. This slide shows a typical structure for a personal computer that used a PCI bus. A bus is a set of common wires through which data, memory, or disk addresses and control signals are transmitted. Most machines make use of it because it drastically cuts down on the amount of wiring that would be required if the various components were directly interconnected. In addition to the machine's main bus, you'll see a SCSI bus and an expansion bus, which allow these devices to share data and control signal paths that are separate from the PCI bus. You can see the different controllers that the system uses. A controller that determines how graphics are displayed on the monitor screen, a controller coordinating access to memory, and a controller determining how data is written on several different disk drives. Ports are connection points through which external devices are connected into the computer's bus. If you have an older computer at home, you would have at least one serial port and at least one parallel port on your computer. The socket into which you would have connected your keyboard's plug is still another example of a port. Currently, these ports would be replaced by USB ports, which now is the most popular standard. The use of standard ports are an advantage that allows us to connect a broad variety of devices to our computers without having to anticipate all these needs when we first buy the machine. The NEC PD765 is an example of a disk controller. For all practical purposes, it is a specialized processor. It has a 16-command language, with the command being executed being stored in a device register. The commands can involve transferring data or various control functions, such as moving the read-write arm, formatting tracks, and so on. Using the PD765 to read or write data will require that we set various parameters, such as block address on the disk, the number of sectors per track, and so on. When the operation is over, we'll get back 23 status and error fields. The processor issues commands to the controller and receives back status data by reading and writing its registers. This is done in one of two ways: by using special input-output commands to read and write I/O port addresses, an address space separate from main memory. The alternative is to reserve a certain number of main memory addresses for input-output devices. Now, input-output commands and status data can be transferred using regular load and store commands. The PC uses a combination of these two methods. Most I/O devices use their own port addresses. Screen contents, however, are stored using the regular address space. This second method is called memory mapped I/O. It makes it easier and faster to transfer data than through I/O ports, but ties up memory addresses and makes the computer more vulnerable to accidental data corruption. This slide shows a partial list of the I/O port addresses on a PC or compatible. While the graphics controller is controlled through a port address, it saves its data at a regular memory address. The typical input-output port has 4 registers: status, control, data in, and data out. The status bits are the ones read by the host system, telling it whether a command was complete, whether there was an error, and so on. The control bits contain instructions issued by the host system, like the one we saw on the PD765. Data in and data out are input and output respectively.